Very good evening and a warm welcome to today's session on Ehrenfest Theorem. My name is Shounak. Just a quick check, is my audio part clear? You can all hear me clear and loud? Can anybody put up a yes or no in the comment box? That would be great. Oh, okay, so the thing is that today's session, Ehrenfest Theorem, is not only a theorem which is related to quantum mechanics or classical mechanics, but this is something which is very deep. And today, as Sunita Williams has returned back her journey back safe on the Earth from her mission in space at ISS, this is a theorem which are kind of a link between what is happening in the microscopic world and what is happening in the macroscopic world. So you can say that on a microscopic scale, quantum mechanics, it governs everything, right? But its macroscopic expectation is something which is, I would say, related to Newtonian mechanics. Here is Sunita Williams, and I've been watching the live telecast since last night. So what I can tell you is that, for example, if you consider the complex physics of aerodynamics, relativity, instrumentation, which more or less large-scale motion, which is governed by classical mechanics, and her homecoming in a way is a manifestation of today's theorem that we will deal. We can say that precision and predictability, which we saw today with Elon Musk's SpaceX taking her safely back to Earth, the physical laws which an astronaut safely guides back are just kind of an alignment with the quantum world or the complexities of the world. All I wanted to say is this, that today's session on Ehrenfest theorem actually proves one thing, very simple, and you all know that. And it is called that physics is something very intuitive. Physics is always not relativity, complex mathematics, quantum mechanics, Schrodinger equation, etc. No, physics is something what you see, what you experience every day when you travel on a bus, when you go to a grocery shop, when you walk on the pavement, when you talk to people, when you see the ceiling fan and everything. So physics is essentially something which is very, very intuitive, and Ehrenfest theorem actually proves that. And we are going to look in that today. And I'm going to tell you it is not only going to be interesting, but this is something which is actually a link between the small and the big. Okay, it is going to be a little bit mathematical, don't worry. I will just put up the equations in different ways, and I will try to explain as easy and as simple as I can. Again, a quick request for those who are watching today's session. Can you just put me a yes that my audio part is clear? I'm waiting for that so that I can proceed. Is the audio part absolutely clear from my side? Because sometimes audios create a disturbance. So I just want to know if anybody can put up a yes on the comment box. That would be great. Okay, great, wonderful. Thank you, Waji. So first of all, let us understand what is Ehrenfest theorem on a very basic level. Then we are going to go into the mathematics because it contains a little bit of different kind of a mathematics. So here you can see overall what we can say. Ehrenfest theorem is a kind of a bridge. When we talk of bridge, I hope you remember that we talked of another bridge which is called the Poisson equation. It was a bridge between the source and the potential. So here Ehrenfest theorem is a bridge between quantum physics and classical physics. And what it tells is that on an average, quantum physics follow the same laws as classical objects. Okay, so here you can see the Ehrenfest theorem. I will explain that. I have made this cartoon because sometimes it finds a little bit complex. These are the four important things that you need to understand. One is that quantum system obeys classical laws in average. That means if you measure the position and momentum of a particle, the average result follows the laws of classical physics. Okay. Second, it tells that expectation value, we will understand that today. On average, quantum particles obeys Newton's law. Third is that when quantum effects like uncertainty, superposition, etc. are very, very small, that means negligible, the system behaves like a classical particle. And finally, what we see is that it bridges between physics and classical physics. I mean to say quantum physics and classical physics. This is all what we can tell in one word. What is Ehrenfest theorem all about? Yeah, hi Raghav. Hello, very good evening. So this is what we call an Ehrenfest. Now I would like to give you an analogy, and I would like to tell you what actually it contains. So first of all, you have understood that it is basically following the Newton's laws of mechanics on a very average level. Okay. Now you see this one. Think of the left hand side. As you see, my presentations a little bit contains a lot of information. Concentrate on the left hand side. You see what it is, an oscillating pendulum. Okay, so pendulum goes back and forth and back and forth. That means if you track the position and momentum over a time, you can predict where the pendulum will go. That means it's going back and forth. You get a position, you get a momentum, and you can exactly say that where the pendulum will go. That is why in classical physics we always use the picture of a pendulum. Okay, simple, right? Now, if you take the other picture on the right hand side, quantum particles, those blue dots on a box. Okay, so what it tells that if that pendulum was supposed to be a quantum particle, its motion would be definitely uncertain, right? Why? Because there is uncertainty. That means we cannot know both the position and momentum of a particle due to Heisenberg's uncertainty principle. Wave particle duality, because particle does not have a single definite position. Instead, it behaves like a wave spread out in space. Then we have probability, because instead of a single trajectory like a classical pendulum going back and forth, we can only predict the probability of finding the position. And there is quantum superposition. It says that the particle can exist in multiple states at once. So these are the problems, right? These are the problems that we can find. Now, if that, what it tells, that if that pendulum were a tiny quantum particle, then Ehrenfest theorem tells out that if you average out many measurements, let me go to the next slide. Yes. If you average out many measurements, then what it tells is that the motion still follows Newton's law on an average. And this is very important. I was telling you, whatever SpaceX has done an incredible job. Whatever it has gone through, it has been incredible. But what it actually tells is that physics is still very intuitive. And it tells that Sunita Williams has come back, and that is what is the predictability part. Predictability part means, just a second. Predictability part means basically what it tells, that it basically tells that where the spaceship will land and how it will come. Okay, before going ahead to show you the Ehrenfest theorem's equation, I would first like to share my screen. Just hold on. Where is my screen? Yeah. Just a second. It's not showing my paintbrush. Just hold on for a second. No, not this one. Okay, anyway, just a second. Share present, share screen. Yeah, I got it. Okay, can you see my screen now? Now, I would just like to explain you, this is actually what the Ehrenfest theorem looks like. Don't worry, I will just tell you what these equations are all about on an average. Just follow me out, then things will be much clearer. This is something very fundamental. Okay, first of all, you see the d by dt, this part. Okay, this d by dt is basically the rate of change of something. It is not the rate of change of anything. It is the rate of change of this one, this box which I am highlighting, right? Is it all clear to you? Okay, this is what is called the expectation values. Okay, I will come to that part. So as you can see, this a with a hat on the top, this is called an operator. An operator is basically shown by a angle bracket. Okay, this is the operator. Okay, next what we see is this 1. This comes out of derivation. I is the complex number because in quantum physics, you know what it happens. H bar is the Planck's constant. Okay. Now here I will first tell you again this A, this is the operator. Okay, this is the operator. Now you see this box bracket, I mean to say this one and this one. This one is called the commutator. We will come to what we mean by commutator. This one is the commutator. So this part is the commutator. This is basically the expectation value. This is the Hamiltonian operator. Okay, then we have got partial derivative of the same operator with respect to time, and we have got again the expectation values. Okay, so here you can see d by dt, that is change of respect with rate of change with respect to the operator. This is basically what it is called. The operator is written in this braces. This you already know. A is basically again an operator. H is the Hamiltonian. Square brackets are basically nothing but the commutators, and this is again the operator. So this is what the Ehrenfest theorem actually tells you. Now let me show you. Now here you can see what it actually shows. Very simple, d by dt. So the time derivative of the expectation value of A, okay, which tells how the expectation value changes over time. How the expectation value changes over time. Partial A by partial T is, it tells that if the operator A depends on time, the term accounts that the dependence of A will, the term will be 0. We will come to that. Okay. AH square brackets, you know, these are the operators, and H is the Hamiltonian. This is what the Ehrenfest theorem looks like. Now here you will see that there are few things that we need to understand. First, we need to understand what is called an operator. Then we need to understand what is called an expectation value. These two things, if it is clear, then we will understand Ehrenfest theorem. Mathematically, I will show you, it will become very, very simple. So I hope you are all enjoying till now the Ehrenfest theorem and what it shows. Okay. First of all, let me give you a very basic understanding in a very simple way. What is a quantum operator? Okay. This is something very important. Okay, now let us imagine that you are basically dealing with one simple quantum system. What do we mean by quantum system? Quantum system means any system that follows quantum mechanics on a very simple way. Okay, so here we are dealing with a single electron. Okay, one electron, and by quantum system we mean that physical system which follows the principles of quantum theory. That means it would have a superposition, it would have an entanglement, it would have probabilistic outcomes. Now, what you see that I am applying a quantum operator, that is X with a hat sign. So what is a quantum operator? Quantum operator means just like mathematics, we have operators. It is a mathematical operator that acts on a quantum state. What is a quantum state? We will come next. Okay. To give measurable physical quantities, that means you can basically measure position and momentum. And in quantum mechanics, all observable properties are represented by operators. So you can say that, for example, if you're dealing in basic arithmetic, a plus and a minus, all those things, these are operators. Okay. In quantum mechanics also, this X hat is nothing but an operator. An operator which actually gives some kind of a measurement. What measurement? That we will look now. Now we have seen with the electron, which is a simple quantum system. Here you can see, now here what you see is that if we apply the operator, the X hat, on a quantum operator to a wave function. Wave function, we have told what we mean by wave function. Wave function is basically anything that gives the information that we know about the system, whether the system is standing, running, whether it is floating, okay, whether it is in space, something like that. So if we apply this quantum operator X hat on the quantum wave function, which is psi, okay, it gives what is called this one, a wave function, which is a kind of a mathematical description of the quantum system. That means it gives a kind of a probability distribution. What is a probability distribution? Simple. It gives us the likelihood to find the electron in a certain area or a region. Here you can see this red arrow, which I have given. This red arrow means that the electron is possibly to be found in this position and less possibly to be found in other position. So technically we call it as a probability distribution, which is given by what is called the Born's rule. that is squaring the amplitude. So that is why I have squared psi x squared. So you now understand, very simple, that we are applying the operator on a wave function. And this wave function is what it is giving. It is basically giving the probability of finding the electron. It is not telling that you will find the electron, but it is saying that most likely, it gives the likelihood that maybe the electron is in this position, which I have mentioned in the red arrow pointing, and the other positions are less likelihood. The electrons cannot be found over there. Now you see here, this one, it is a very simple thing. It is called bra and a ket operation. So if you apply the operator to a wave function psi, it looks like this. So what it means, let us understand the left hand side. It means that if you are taking or making a measurement, the operator is labeled as x as position along the x-axis with a nice little hat on the top, which denotes it to be an operator. So here you can see from the from this part of the slide that this is similar to applying a measurement. So you just measure something simple. You measure with a tape, you measure with a rod. So you measure something. Now you see, if I take this kind of a box, okay, and if I tell that if I make a measurement, how long it is, maybe it is 2 centimeter. Okay, this is an exact measurement. Remember, 2 centimeter. It is an exact measurement. Now, if I put a kind of a, say, for example, what will I put? Okay, let me take my pen drive. Okay, now if I put my pen drive over here, you can see this. Then I can tell where it is. I can tell the pen drive is here in this position. Okay, this is the exact position as per classical physics. The pen drive is here. Now, quantum physics says no, the pen drive can be here, 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 here. It can be anywhere. So making a measurement is pretty simple in case of classical physics, because you can pinpoint and tell this is where the ball is. That is what I am showing in this slide. Okay, you can see that in classical mechanics, making a measurement is simple. So I can say that the ball is either in any of the position, for example, at point 3. But when we are making a quantum measurement, then it becomes difficult. So how can we know to find the probability distribution so that there is a fair chance and a likelihood to find the position? Note that it does not only appear to position, but to other areas also. Okay, so here I am giving a likelihood that the ball may be here, 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 but more or less the ball will be in this position. So the right hand side, this red arrow pointing on the graph tells that the position is here. Now here is a catch. This is, I am telling, prior to making the measurement. Okay, this is something which is prior to making the measurement. So the ball can be here, here, or here. But what happens when we make the measurement? Actually, what happens? That is a big problem. Here you see, on the left-hand side of the first graph, what you can see is that the before measurement, it can be here, here, or here. But after making the measurement, it causes a fundamental change in our wave function, which is called the collapse of the wave function. Medini Chaudhary. Okay, yeah, hi, Medini. Thank you. So where it can be, okay, it can actually collapse. So remember, the wave function has changed because probability distribution has changed. Earlier, you see the probability distribution was this one. Okay, but as soon as we make the measurement, the probability distribution is this one. That means the wave function has changed because the probability distribution has changed. So making a measurement in quantum mechanics has a serious consequence, has a serious effect, which is not in case of a classical system. Okay, and as I have shown you, the probability distribution spreads out. If you look at the bottom of the slide, then you will see the spreading of the probability distribution is guided by what is called the Schrodinger equation. Now remember one thing also, that whenever we are making the measurement, particularly when we make the measurement, the probability distribution and the wave function collapses, and the probability also spreads out in a fraction of a second. In a fraction of a second, it changes out. So here I have shown you that the probability distribution actually spreads out. So here is an important note which most of the students make a confusion, that it is not the electron collapses, it is the wave function collapses. And how the wave function evolves over time, that means that spreading, etc., is guided by Schrodinger equation. And this Schrodinger equation also has got a Hamiltonian operator, which I have shown in this part of the slide. Okay, so now you will see how easy it becomes. Here you can see that it simply multiplies the function by x. So x hat psi x is equal to x psi equal to x. This means that we are just scaling the factor. X is just a scaling factor. Momentum operator, in the position, momentum operator is a differential operator, as you can see, acting on a wave function. So this tells how the wave function changes with position, linking momentum to the shape of the psi x. And here also you can see there is a Hamiltonian operator which gives the total energy. We have learned that in Lagrangian. Acting on psi x gives the energy of the system. And this is the Schrodinger equation which determines how the system actually evolves. Okay, this part of the presentation shows that. Now remember that when we talk of making a measurement, it is not a conscious human being or an animal or any conscious being which is making being present. It is the interaction of our system and the measurement that makes the difference. So here I would like to point out there is no human being. This is why, there are many ultra pseudo science books. I laugh when I read those books, like is quantum mechanics has got a conscious human being, and is consciousness? No, nothing. There is no conscious human being which is making a measurement and it is causing a collapse of the wave function. It is just that the interaction changes. So here is a confusion. Is there a conscious human being? No, absolutely not. There is no conscious human being as per Copenhagen interpretation. It is the interaction which actually changes. Now let me show you that wave function collapse. This is the common misconception. So remember that there is no that conscious observer. There is no conscious observer which plays a role in a wave function collapse. Now, this idea actually came because of the difficulty of defining what constitutes a measurement in quantum mechanics. So some took this as a meaning that a human being is responsible. No. Here you will see that there is a concept called decoherence. Okay. The collapse, coherence means what? Which actually acts logically. So we say that it is a coherent idea. Coherent means which has got a logic, which has got a meaning. Decoherent means which has got no meaning. Okay. Okay, so let me go and check the meaning once. Coherent meaning. Yeah, coherent means, ability to talk ideas or thoughts. Yeah, I am right. So decoherent means which has got no idea. So here you can see I've just drawn to these two slides. One is the wave function collapse. So that is an idea. The collapse occurs due to decoherence and the interaction with the macroscopic system. I will just give you a very simple example. I hope you will understand. Now here you can see what it is. Imagine a spinning coin. Before you look it is in a superposition or heads and tails. But the moment you measure, it is basically collapsing. So if the coin falls in a water interacting with the environment, the ripple makes it settle to either heads or tails. And this is basically what is called quantum decoherence. Okay, let me show you the next part. Things will become much easier. Here you can see, I would like to show you this quantum decoherence. So quantum decoherence is basically, imagine that these are ripples. It forces the system to lose its quantum weirdness. Okay. So the teams, for example, if I can say the team's initial coherence and shared vision was strong, but disagreements over a strategy led to decoherence. Similar word. So a quantum system exists in a superposition of states. For example, psi is the quantum state, psi1 and psi2 are possible states, and c1 and c2 are the probability amplitudes which you know. And the probability of measuring the system is given by Bond's rule. I have talked earlier, you square the amplitude. So what happens here is when the quantum system interacts with macroscopic measuring device, it can be a scale, microscope, glass, laser beam, whatever. So when the system interacts with a microscopic measuring device, the delicate quantum superposition is destroyed by the interaction with the measurement or the environment, and this is known as quantum decoherence, where the system becomes entangled with the measurement apparatus. I hope that can make things clear, right? Now you see the next part. Here you will understand the quantum system. I have given those simple dots. So the quantum systems interacts with those tiny particles around, okay, and the wave function collapses into one of those possible outcomes, okay. So once measured, the system is no longer in a quantum superposition. It takes a definite value. Repeating the measurement, it gives the same result. So here I have written when a measurement is measured, so you see the psi, and the measurement is either psi1 or psi2, the wave function, with a probability of C1 square or C2, which is the probability amplitude by Bond's rule. So if the system interacts with the environment, it becomes entangled with the environment state E1 and E2. And after decoherence, that is the classical behavior, the system chooses a definite state and the quantum effects disappear and it just behaves like a classical object. So what we can tell from now is that before measurement, quantum superposition exists. Measurement or decoherence destroys superposition and causes the system to take a definite state. And mathematically, this is used using what we call operators that we are learning right now. So here is a quick summary of what I was telling. The collapse of the wave function is caused by the interaction between quantum system and the measuring devices. Okay. So this is what actually it leads to. Now, here when we are measuring, so we are measuring the quantum system with what we call operators. Now here it comes a very important part. Now, if we try to make a double measurement, okay, one measurement and second measurement, this becomes very difficult. So what is 2 plus 2? 2 plus 2 will always be equals to 4. So, or say what is example, 3 multiplied by 2 is 6 and 2 multiplied by 3 is also 6. Okay, both of them are giving the 6. That means if you are making any measurement, the way we make the measurement does not make any change as far as classical physics is concerned. But this is going to change in quantum physics. So that is why I have written here that order in which we make the measurements actually takes a kind of a change. And this is actually dealt with what is called commutator. And this is the second and the most important part of our learning. So we will learn here what is a commutator and why these differences actually creates a change in the quantum measurement. So here you can see what I have told is that in classical physics, measuring position and momentum does not change the system. So if, for example, position is x equal to 5 and momentum p is equal to 10, then if we swap the order 5 to 10 and 10 to 5, it is the same. So x times p is equal to p times x. Okay, but here you will see a difference. Measuring the position of quantum system changes the wave function of the system. So when you measure the momentum afterwards, we are making the measurement in a totally different wave function. So here you can see that measuring the position of a quantum system, for say for example x and psi. So p and x psi, when it collapses to the wave function, it becomes different. Before the wave function collapse, it is different. After the wave function collapse, it is different. So here that is why I have written px psi is not the same as finding the momentum first and then the position. So px psi is not the same as xp psi, whereas in classical physics, xp is equal to px. So remember, when we measure the momentum afterwards, we are measuring in a totally different wave function and the wave function has totally changed. I hope this is getting clearer and clear. Here you can see the difference. Measuring what I have been, take a note on the left hand side of the slide. Measuring the position first on the right hand side, P, measuring the position first and then the momentum can give you different result when you are measuring the momentum first and then the position. So P measuring first and measuring X is not equal to X measuring first and P next. So we know which operation is done first. As we can see, the one which is nearest to the wave function is the one which is done first. So P is nearest to psi, so that is first. The equation on the left hand side, X is nearest to the position psi, that means X is first. Okay, so this is what the difference is. So now as Px psi is not equal to Xp psi, that means subtracting would also not give us 0, whereas classical physics it gives us 0. That is why I have given 3 times 5 minus 5 times 3, 15 minus 15 equal to 0, but here it is not happening. So what we do is that we factorize or put out the psi. I have put the psi out of the entire equation, and we get this one, which I have written with a down arrow, commutator. Okay, commutators are actually written in square brackets. Now concentrate on the right hand side of the slide. Commutators are written in square brackets around the quantities, and commutators actually tell us the order in which we make the measurement. So here the position and momentum, it does not matter as it is 0. But what about the other way around? Now here we have measured position and momentum. Look in this part of the slide. Here you can see that measuring O first and then P gives the same result as measuring P first and then O. Here it is different. Measuring X first and then P is not the same as measuring P first and then X. But in this part, you can see measuring O part first and then P gives the same result as measuring P first and O. In that case, the commutator would be 0. So in one case, the commutator can be 0. In other case, it cannot be 0. So if we now break down, you see that X is the position operator, Px is the momentum operator, and commutator is Xpx. This measures whether two operators commute, meaning whether their order matters or not. Now here, since the commutator is not 0, we call it as a non-zero commutator. It tells us that the position and momentum cannot be measured simultaneously, and that is the reason we get the Heisenberg's uncertainty principle. So OP minus PO is equal to 0. That means they do commute. That means 9 multiplied by 2 is equal to 2 multiplied by 9. That is why I say multiplication is commutative. And this measures whether the two operators are commutative or not. Let me give you a very simple example through matrix multiplication. You see this. This is an example where the commuting operators, this one AB equals to BA. On the other hand, you see XP minus PX is something different. So here the matrices do commute, here the matrices do not commute. Very simple. In linear algebra, we find this. So what we have learned till now, let us make a quick summary. We have learned that order equal to, if OP equals to 0, then order of measurement does not matter. If it is not 0, it matters. In classical physics, the order of measuring position and momentum does not matter. Here, commutator helps us to determine whether the order matters or not. Okay, commuting operators, for example, momentum, etc., allow simultaneous precise measurements. And in quantum mechanics, if two observables do not commute, that means in different orders leading to different results. So this actually lets our understanding in what is a commutator, right, and what is an operator. Operator is very simple. It is a measurement device. Commutators actually helps us to know that whether they will give the same result or different result. Now we come to the next part where we will understand a little bit of what is called an expectation value. This is simple and very important. So here you can see what I'm trying to show you as what is expectation value. Now say for example, again we are studying the wave function, that is we are studying a simple electron. Now here you can see that again, as I told you, it gives you the likelihood because quantum mechanics is probabilistic in nature. So the expectation value represents the average outcome of a measurement if the same experiment is repeated and repeated and repeated. What it tells is the average outcome. That means it helps in calculation by providing a way to determine observable quantities like position, momentum, energy, any form of a quantum state. That means it is most likely to be found at that position and less likely to be found at that other position. So in this case, the probability distribution is symmetric. As you can see, it is a bell type of a curve, right? These are all bell curves. So that is why the probability distribution is something symmetric. Hence, the expectation value is just the average value. You can see I have taken the middle position. What is that? That is the average value. So expectation value is average value, but it is not always. Let us consider this kind of a probability distribution. You can see the left-hand side, one bell curve and another bell curve. You can see that. Okay. So if we get a probability distribution like this, then we cannot find the electron here or here. So expectation value, remember, is not always the likelihood of finding the electron, but rather we write the expectation value in angular brackets like this one. Okay. So what it tells is that the general definition is that it has got a bra, which is this one, and it has got a ket, which is a psi, that is a wave function. Now, we have seen that the expectation values is not where we can find the likelihood of the electron. Then why will you learn about expectation values, right? So in quantum physics, there can be fluctuations due to uncertainty principle. So Ehrenfest theorem actually holds approximately what quantum fluctuations are small. So with this now in hand, I hope you can understand this one. So here you can see in yellow I have written, Ehrenfest theorem actually shows that the expectation value of quantum operators obey what are called Newton's laws. So this is actually what is called the expectation value. So expectation value is basically what is called, is to find the electron, it is the weighted average. Okay. Now we take all the learnings. Okay. Whatever we have learned expectation values, we have learned quantum operators, we have learned commutators. Now we will all take and finalize in this Ehrenfest theorem. So hold on, we are coming to a very interesting part of our session today. So here you can see just a quick repetition. So you know that we have learned x, p, and h, position, momentum, and Hamiltonian operator. We can, x and p is the position and momentum operator, and x is the expectation value. Commutators are square brackets and expectation value are angular brackets. So A is basically what? It is basically a operator. It is just a general operator. Okay. In Hamiltonian, we get the kinetic and the potential energy. Right? And here we are getting the expectation value. It is just A is just an operator. It has nothing specific. Remember, A is nothing specific. We will just see that how this A gets replaced with any other B or C. Okay. So here you can see that if I substitute A with X. Okay. So if I substitute A with X, the Ehrenfest theorem becomes this. And if I substitute A with P, momentum, the Ehrenfest theorem becomes this. Simple. So what it actually tells is that it is just a placeholder. If we change things, the entire Ehrenfest theorem actually changes. Okay. So now you see, if I put in here, what you can get from here. Right. So here you can see that you already know this d by dt. It represents the time derivative of the expectation operator, A. Physically, it tells that how the average position of the quantum particles changes. So d by dt is how much the quantity changes with respect to time. Here we are finding the rate of change with respect to time of the expectation value. The partial derivatives actually tells, it actually represents explicitly on the time dependence of x. Okay. So when we say explicitly on time, I am trying to mean is that if an operator itself changes with time directly, it has explicit time dependence. If an operator remains the same all the time, then its partial derivative with respect to time will be 0. So mathematically, if an operator does not explicitly depend on time, then partial A by partial t will be 0, obviously. That means that if we take the derivative of the operator A with respect to time, it gives 0 because A itself does not change with time unless it is influenced by wave function or evolution. So that is why it is important. If an operator itself changes with time directly, it has explicit time dependence. If an operator remains same, then the partial derivative will be 0. And here you can see that operators correspond, and how we make the measurement, either position or momentum, does not change with time. So how we make the measurement, either position or with time? That is the biggest question. Now here you can see what I'm trying to show you is that we have seen this one, the position operator, the momentum operator we already know, right? So that we already know. Momentum operator, position operator we have also seen. So what we are interested is the expectation value of the commutator between A and H. Now here we are substituting A for the position operator, and what we see is this result. So what happens next is that I am substituting A, or rather I am putting the value of X in terms of A. And what happens next I will like to show you, but those who are not interested particularly in mathematics, you can skip this part. I'm sorry, I'm having my evening coffee because after that again I have a class. So what happens next? So those who wants to skip this part, you can. I have done very simple calculation. I have taken the Ehrenfest theorem. I have substituted the value of A, and again I have resubstituted the value of X, A with X, which actually reduces the amount to 0. Here you can see. And then I have calculated the commutator, which actually represents this. So here you can see, you can skip this part if you don't want. X represents the position operator, Vx represents the potential energy. The two operators A and B commute. Why? Because if their commute is 0, this means that applying them in any order gives the same result. Now, why does X commute with Vx? Since Vx is just a function of X, that means it means that multiplying Vx does not change order of multiplication. So this happens, both are built from the same operator. So in Ehrenfest theorem, we need a commutator. So Hamiltonian energy H contains the potential energy term Vx, and the commutator with X simplifies. So this means that we only need to focus on computing the commutator, which I have done in this part. The Vx cancels out. Here you can see the Vx actually cancels out. So we compute the XH, and since Vx and Vx commute, we only need to compute this part, and using the commutator relation, we put this value and we get this value. And next I will just go quickly. Here you can see, substituting these values, we ultimately get to this one. So what, now you understand what it tells, P by M. So what it tells is basically, if we rate of change of expectation value of the position of our electron. Now what I am talking of the central part. You see a lot of arrows here. So I'm trying to explain this part. So substituting back, it gives P by M. But what it tells? It tells that the rate of change of the expectation value of the position of our electron. Position means, what I am trying to tell is this one, X. So the rate, again I am repeating, the rate of change of the expectation value of the position of our electron multiplied by mass m of the electron is equal to its expectation value of its momentum. Right? It is so simple, and it is just as simple as classical physics. So we have taken the rate of change. Again I am repeating. So you see d by dt is basically the rate of change. You already know that from pure calculus. So the d by dt is the rate of change of what? Of the expectation value, that is X with a hat. So rate of change of the expectation value of the position of the electron. Position of the electron is X. So rate of change of the expectation value of the position of an electron multiplied by mass m, which is the mass of the electron, is equal to its expectation value. This is the P is the expectation value of its momentum. So analogous, we can say, just in classical physics, similarly, rate of change of the position of a ball with respect to time is the same thing as its velocity. You have to agree to this, isn't it? The rate of change of the position with respect to time is the same as its velocity. When we multiply by its mass, we find its momentum. So in Ehrenfest theorem also, we deal with expectation values, whereas in classical physics, we know the exact position and momentum. right? So although quantum physics is weird and probabilistic, when we look at expectation values, it actually comes back to what is called classical physics. So here you can see in this part of the slide that the average expectation of the position momentum obeys the same classical mv is equal to p. Here you can see mv is equal to p in this part, and here also in Ehrenfest theorem it says the same thing. M d by dt of x is equal to p. And here also m dx by dt m equals to mv is equal to phi. That means it is the same thing as in classical physics. It follows on the on the quantum level also. I was really thrilled when I actually discovered this part. I mean to say, when I read much years earlier, but when I was making this part of the video, I was really thrilled. So from here, we can summarize. This is the summary. Okay. So what we can tell from here? What we can tell from here are these few things. Okay. Let me go back to the earlier slide. I have few things left also. So here you can see that while individual quantum particles behave probabilistically, the average expectation value of their position and momentum obeys classical equations of motion. This means that quantum mechanics on average transitions or gets into classical physics. So Ehrenfest theorem shows d by dt of x equals to p by m. This is exactly how classical velocity relates to momentum, v equals to p by m. If we substitute momentum p for a in Ehrenfest theorem, we get this. And this actually matches with Newton's second law. Here now you can see this one. This is the final part of our summary. So I bet I would request you, all of you, to read it properly. Okay. So here you can see that on the right hand side again. So earlier what we have done, okay, let me go back. Okay, earlier what we have done. Okay, let me go back. Yeah. So here you can see I have substituted x, that is position, for the operator a. And we got back the entire equation, which actually shows this one. Next, and next. Okay. Now, if I substitute classical physics, now here you can see on the right hand side of the slide, if I substitute momentum in place of a, that also I can do. Instead of position, I can also substitute momentum. So if I substitute momentum, then it will give this one, which you can see on the right hand side of your screen. D by dt of p equals to minus dv by dx. So if we substitute p for a in Ehrenfest theorem, we get this one. And this actually matches with Newton's second law, F equals to minus dv by dx, meaning that the expectation value of momentum changed according to the classical force. So this is the summary which you can read, that just like the position, Ehrenfest theorem for momentum also leads to Newton's classical law on average. So by substituting momentum in Ehrenfest theorem, we recover Newton's second law in expectation values. And this actually tells us that on average, quantum system obeys classical physics when look at their macroscopic behavior. So you can actually substitute x, position, for a, and get this classical position, momentum, velocity. And here you can, I have substituted v. I'm not shown the calculation totally, but it actually leads to F equals to minus dv by dx, which is again Newton's second law. Now, can you tell me in this picture which one is Paul Ehrenfest? Which one is Paul Ehrenfest? Any guess? You can put it in the comment box. Okay, other than Einstein, who are those people? Other than Einstein, can you recognize these people? Anyway, so thank you very much for attending today's session, and I hope that you have liked it. Please do let me know in the comment box, and do not miss the 30th March podcast on this channel. A very important person is coming, a very reputed scholar from Jadavpur University, and she would be speaking on general theory of relativity. So please do not miss the podcast on 30th of April. I will make the announcement in a few days' time, but it is very, very important. 30th of April, right on this channel, Physics for Students, starting 8 p.m. Indian Standard Time. So I hope you liked today's session. I always wait for your reactions. It would be great if you can put up the reactions over here. So Ehrenfest theorem actually again bridges the gap, I won't say a gap, bridges between classical and modern physics. And what Sunita Williams came today, that's on a very intuitive ground. Physics or spacecraft or whatever we see is actually nothing but an intuitive way of understanding. If you throw a ball, it will hit. If you throw a ball on the pond, it will create ripples. So whatever you do is actually very intuitive. And Ehrenfest theorem actually tells that classical physics and quantum physics, or rather I would say quantum physics comes from classical physics on a very intuitive ground, and it follows Newton's laws of motion. Thank you very much for watching today's podcast. Thank you. And we'll be back with few more videos and an important podcast coming up on the 30th of March on this channel. Please put up your comment and do subscribe to my channel, Physics for Students, and click on the bell icon to get notified with all the important and fun-loving great videos which I try to make and educate the young people. Thank you very much.